There is an LC circuit where L is the inductor and C is the capacitor, and we supply this circuit with the alternating voltage here. The main goal is to show that the resonant frequency of this circuit is given by this formula. The resonant frequency depends on the value of the inductor and capacitor. So if this product is big, then the resonant frequency is small. If this is small, the resonant frequency is big. We have a reverse proportion connection here in this formula. And the first, what we need to do is to find the total impedance in the whole circuit. And we use basic relationships from electrodynamics. The current that flows into the capacitor is given by the product of the capacitor times the derivative of the voltage of the capacitor with respect to time. Now, because we are talking about impedance, we take the Fourier transform of these quantities here. We use J not to conflate it with the current, so the J is the square root of -1. And also I take the Fourier transform of this derivative here. Is the integral from 0 to infinity of the derivative times the kernel of this transform, which is e to the minus j omega t dt. Now here I just have to do integration by parts. This term vanishes here, goes to 0. And finally I get that in this equal I have that j times omega, which is the pulsation times the capacity times the Fourier transformed voltage, which is V with subscript C j omega. The current, the Fourier transform current equals j omega C times the Fourier transform voltage. Here in this case, we have to go back to the Ohm's law, where the current equals the ratio is a fraction of the voltage divided by the resistor. And from here, the resistor equals the voltage divided by the intensity of the current. The impedance of the capacitor X, we use the capital X subscript C, is 1 divided by j omega C. We multiply with the conjugate and we obtain that the numerator is minus j divided by omega c. And this is the impedance of the capacitor. The voltage applied to the inductor is the value of the inductor times the rate of change of the current with respect to t. I take the Fourier transform. This is L here. Here now I have to do integration by parts. This term vanishes, and I always have that j omega L times the Fourier transform of the current in the capacitor, which is IL j omega. From here I have that the voltage, the Fourier transform voltage equals j omega L times the Fourier transform current. From here I take that the voltage divided by the Fourier transform voltage divided by the Fourier transform current. The impedance in the inductor is j omega L. The total impedance is the impedance of the capacitor plus the impedance of the inductor equal to 0. This is j omega L minus j divided by omega c equal to 0. This should be equal to 0. We know that omega is 2 times pi times the frequency. The resonant frequency is 1 divided by 2 times pi times the square root of the product of the value of the inductor and the value of the capacitor.